The night the sky threw a rock back. It started with a flash over the western Pacific on January 8, 2014. The U.S. Department of Defense watched it the way they watch everything bright and fast. Infrared sensors registered a fireball slicing into the atmosphere at a speed that didn't fit the usual charts. In the public NASA CNEOS catalog, the event later appeared as a small meteor with a strange label, hyperbolic pre-atmospheric velocity, faster than the sun's gravity could reel back. Most meteors are bound visitors. This one, if the numbers held, came from interstellar space. There was a catch. The numbers were blurrier than the community liked. The crucial error bars on velocity were classified, hidden inside systems built for missile warning, not for peer-reviewed science. You could see the dot on the plot, but not the shadow that told you how sure the dot really was. For years, that uncertainty kept the event, cataloged as CNEOS 2014-0108, stuck in a strange limbo. Interesting, tempting, not publishable without a fight. Avi Loeb saw the dot and couldn't stop thinking about it. By 2019, he and his student Amir Surej had dug through the catalog and flagged the outlier. The path traced back on a hyperbolic track. The speed before atmospheric drag still looked too high to be from our solar family. If that was true, Oumuamua wasn't just a meteor. It was a messenger from another star, the first interstellar object to hit Earth we'd ever recorded. But the journal reviewers wanted those error bars. Without them, the claim stalled. For Loeb, this was déjà vu. 2 years earlier, Oumuamua had torn through our system and made careful scientists uncomfortable. He'd watched the debate turn rigid when the data stayed weird. Now he faced the same problem in a different disguise: military sensors with answers locked behind classification. Open science runs on transparency. Defense systems run on secrecy. How do you build consensus when the evidence sits behind a badge? Then in April 2022, something unusual happened. The U.S. Space Command sent a letter signed by a senior scientist stating, with high confidence, 999%, that the meteor's pre-atmospheric speed was indeed high enough to be interstellar. The key uncertainty numbers had been reviewed within the classified system. The physics checked out. In one paragraph, the event jumped from rumor to recognized outlier. It didn't settle every question, but it moved the goalposts. The first known interstellar meteor had hit Earth. That validation came with a new set of stakes. If Oumuamua was interstellar, what was it made of? The light curve from the 2D sensors suggested it didn't fragment the way typical meteors do. It held together deeper into the atmosphere, hinting at unusual strength. Was that a quirk of entry angle and size, or a sign of material we didn't usually see? Without fragments in hand, nobody could say. The speed and trajectory were one kind of extraordinary. Composition would be another. Loeb didn't want to wait for another memo. He moved. He started mapping the fireball's final seconds, cross-referencing wind patterns, ocean currents, and drift models to estimate where debris, microscopic and macroscopic, might settle on the seafloor north of Papua New Guinea. He gave the object a name, Oumuamua, and a target, a fall ellipse, a narrow swath of ocean where spherules, tiny melted droplets, could have rained down, cooled, and sunk. There were obvious criticisms. The CNEOS data, even with the classified review, wasn't collected for geology. Sensor calibration remained opaque. The ocean is full of industrial residue, ship emissions, steel slag, paint, even cosmic dust from countless ordinary meteors. Searching a deep, windy patch of ocean for particles smaller than a peppercorn sounded like a needle-in-haystack story without the haystack map. But the potential payoff changed the calculus. If you could bring up metal that chemically and isotopically matched an interstellar origin and showed unusual strength, you might pull the debate into a lab where opinions matter less than spectra. Loeb framed it plainly. If the numbers say interstellar, then the ocean floor is an archive, and archives can be read. He raised funds, assembled a small team under the Galileo Project banner, and contracted a ship with a simple plan: drag a magnetic sled over the mapped corridor, sieve the collected sediment, and separate out spherules for analysis. It wasn't elegant, but it was testable. Either you find a concentration spike in that line compared to control transects, or you don't. Meanwhile, in the background, caution hummed. The scientific community knows how easy it is to jump at a shiny anomaly. The 1996 Martian meteorite with supposed microfossils, the Viking life experiment ambiguity, decades of UFO claims, each left bruises. The pushback came in careful language. Confidence in origin isn't the same as confidence in composition. Without a clean chain of custody and rigorous contamination controls, any positive finding could evaporate on contact with peer review. And the critics had a point. Extraordinary claims don't just demand extraordinary evidence, they demand ordinary procedures executed flawlessly. But the clock was ticking. Currents shift, sediments move, and attention wanders. Loeb argued that the search itself could be iterative, collect, analyze, publish methods, invite replication. If the first pass found nothing, that was an answer. If it found something, the real work would begin. What he couldn't accept was paralysis. An interstellar meteor had happened over water shallow enough to reach. Doing nothing felt like turning your back on a once-in-a-generation chance. To understand why he moved that fast, and why his framing split rooms, we need to go back 5 years earlier, to an object that acted like it had a mind of its own. Oumuamua, the thing that didn't behave. In October 2017, a telescope in Hawaii flagged a moving speck sliding against the stars. Panastarrs does this nightly, but this track had a weird curve, too fast, too sharp, the kind of arc that says this visitor wasn't bound to the sun. Astronomers ran the orbit and blinked. It came from outside the solar system on a hyperbolic path. They called it 1I/Oumuamua, Scout in Hawaiian, and immediately it refused to act like anything in the category list. Comets usually announce themselves with drama, gas jets, a glowing coma, dust tails that bloom as sunlight cooks ices. Oumuamua gave nothing obvious. No fuzzy halo, no tail, just a faint tumbling point whose brightness rose and fell in a pattern that hinted at an odd shape. The light curve stretched by a factor of roughly 10, suggesting something elongated or very flat. People argued a cigar, others argued a pancake. Both were guesses standing on flickers of light. Then came the twist that pushed it from interesting to unsettling. As it left the inner solar system, its trajectory changed in a way gravity alone couldn't explain. The acceleration was small but real, measurable across multiple observations. Comets do this when outgassing acts like a thruster, but if gas was pushing, where was the gas? The Spitzer Space Telescope looked for warm dust and typical volatiles like CO and CO2. ALMA checked for radio signatures. The detections didn't show the usual suspects. Oumuamua kept moving as if something was nudging it, and nobody could point to a visible engine. Here's where Loeb stepped onto the stage. If there's no coma and the push is real, he argued, then one simple explanation is sunlight itself. Not magical sunlight, radiation pressure, the steady push of photons. For radiation pressure to matter, the object must have a high area-to-mass ratio, like a thin sheet catching wind. A natural rock with that geometry is hard to conjure. A manufactured light sail is easier to picture. He wrote it plainly. Oumuamua could be artificial. The mainstream recoiled, not because it's impossible, but because it's a leap. Astrophysics tries natural first and exhausts the inventory. So the community started inventing natural shapes and materials that could mimic a sail. One proposal imagined a hydrogen iceberg, a frozen puff that sublimates invisibly, providing thrust without leaving a detectable trail. Another argued for a nitrogen shard, chipped from a Pluto-like world, its ices venting quietly. Others proposed a fractal, extremely porous dust aggregate, featherweight but voluminous, pushed by light like dandelion fluff. Each idea solved a piece and broke somewhere else. Hydrogen ice doesn't survive long in interstellar space. Cosmic rays heat and eroded over millions of years. Nitrogen shards might form, but you need to explain how you produce enough of them and keep them intact. A fluffy fractal could be pushed by light, but could it survive close passes to the sun without disintegrating? Meanwhile, the non-detections of carbon-bearing volatiles forced tweaks to models. Maybe CO2 was locked up, maybe outgassing was directional, maybe dust grains were larger than expected and stayed invisible. Maybe did a lot of work. Loeb leaned into the discomfort. He wasn't claiming proof. He was saying the data made technology a live hypothesis that deserved a seat at the table. But culture matters. The field had scars from past claims that ran ahead of evidence. So reviewers kept asking for one more natural pathway before letting light sail sit near the front. The debate hardened along familiar lines. If you open the door to artificial, you need extraordinary evidence. If you keep the door shut, you risk ignoring a clue because it feels taboo. The human moments in those months were small and telling. Graduate students whispered about applying to work on Oumuamua, but worried their advisors would steer them to safer topics. Telescope time got parceled to projects that could promise conventional returns. The public, though, devoured the mystery. Every press briefing had to balance, "We don't know," with "We're not saying aliens," a sentence that convinces no one and angers both sides. Meanwhile, the clock kept running. Oumuamua was faint and fading. No mission could catch it on short notice. We had a once-only glimpse and a mountain of inferences built from a handful of photometric points and follow-up observations. That scarcity is what made Loeb impatient. If you can't go to it, find the next one, or find something it left behind. Which is why, when that 2014 Fireball's data got a second look years later, Loeb felt a pattern forming. Two interstellar signals, both misfitting their boxes. What nobody knew at the time was how sticky the Oumuamua arguments would be. Papers would keep arriving, reanalyzing thermal properties, pushing updated sublimation models, and revisiting non-gravitational acceleration with new assumptions about outgassing efficiencies. Loeb would rebut, sometimes sharply, pointing out where parameters were tuned to get the desired result. The core tension stayed. Either a natural object with rare properties, or an engineered object with ordinary physics masquerading as rarity. Two anomalies don't answer intent, but two anomalies change your search strategy. Loeb started saying it out loud. You can debate models forever, or you can go get evidence you can hold. He chose the latter, because if Oumuamua whispered a question with its silent push, maybe the ocean floor held a reply. The Pentagon letter that changed the odds. 3 years after Loeb and Suraj flagged the outlier and hit the wall of classification, an email thread turned into a lifeline. In April 2022, the U.S. Space Command released a short letter on official letterhead, signed by Lt. Gen. John E. Shaw and coordinated with Space Force scientists. It referenced the January 2014 fireball and used a phrase the community hadn't seen before in this context: 99.999% confidence that the object's pre-atmospheric velocity was high enough to be interstellar. That number wasn't plucked from enthusiasm. It came from an internal review of the classified error bars, the same uncertainties journals had asked to see. The subtext landed hard. The DoD had rerun the astrometric solution with access to the raw sensor characteristics, the calibration tables, the timing accuracy, everything that turns a flash into physics. The letter, later accompanied by a note from the chief scientist of space operations, said the uncertainties were small enough to preserve the hyperbolic solution. In plain English, the speed wasn't a rounding error. The object really arrived from beyond the sun's grasp. Legitimacy arrived with an asterisk. Scientists want data, not assurances. A confident statement is a bridge, but it's not the road. Without the underlying measurements, peer reviewers can't replicate the exact fit, test alternative noise models, or probe systematics. Some welcomed the letter as the necessary stamp to treat IM-1 as interstellar. Others saw it as authority substituting for transparency. Both reactions were reasonable. The sensors weren't built for public science, and declassifying their guts carries national security baggage. That tension, reliability nested inside secrecy, became the new battleground. Loeb treated the letter like a starting gun. He wrote that the interstellar designation crossed the threshold for action. If origin is settled to that confidence, composition becomes the urgent question. He sketched the expedition in memos and blog posts, moving from idea to procurement. The Galileo Project, his research effort built to study unusual aerial and astronomical phenomena with open methods, would organize the search. He began calling the meteor IM-1, Interstellar Meteor 1, framing it as the first of a class to be studied rather than a one-off curiosity. Inside departments, eyebrows rose. Confidence isn't composition. Confirming an interstellar speed doesn't tell you if you're chasing stainless steel, a rare cosmic alloy, or just a tough natural rock that took a lucky path. Critics pointed to the lack of peer-reviewed numbers on luminous efficiency and fragmentation modeling for this event. If you infer strength from a light curve, you're assuming how brightness maps to kinetic energy release, and those assumptions can mislead if the object was small, entered at a shallow angle, or fragmented outside the instrument's sensitivity. The reply from Loeb's side was pragmatic. Uncertainty is exactly why you go get samples and test them. He argued that oceanic micrometeor spherules are a known class of byproduct, tiny beads formed when an incoming object melts and splashes in the atmosphere, then cools and sinks. If IM-1 shed a hail of droplets along its final track, the seafloor directly downrange should hold a statistically higher concentration than background. That's a testable prediction. Map the fall ellipse using wind shear and current drift models, drag a magnetic sled along transects, and compare yields with control lines outside the corridor. If there's a spike, proceed to lab. If there isn't, publish the null. Meanwhile, the peer review problem didn't evaporate. Journals want pre-registered methods, contamination controls, and chain of custody documentation that can withstand hostile reading. Loeb's team began drafting protocols. Stainless hardware rinsed in ultra-pure water, clean room handling, blank runs to quantify shipborne contaminants, and independent labs for elemental and isotopic work. He courted funders willing to tolerate reputational risk and reminded them of the asymmetry. A small expedition could, in principle, produce the first physical material from an interstellar object ever found on Earth. The Pentagon letter also changed the field's conversation about precedent. Until then, the only certified interstellar visitor was Oumuamua, seen and lost to distance. Now, a second interstellar object was on the books, this one with an impact location within reach of a ship. That combination, confidence plus accessibility, was rare. It nudged cautious scientists to say, at minimum, this warrants a look. Pushback hardened in parallel. Some meteor experts warned that 2D light curves are not designed to constrain strength with the precision being implied. Others emphasized how many sources can produce metallic spherules, industrial fly ash, ship paint, slag, and how easy it is to overinterpret a handful of unusual beads. The sensible path looked slow. Wait for declassification. Wait for corroborating civilian sensors. Wait for independent confirmation. Loeb chose momentum. The letter didn't end the debate. It reset the stakes. If you believe knowledge advances by confronting uncertainty with measurements, you go to sea. If you believe the risk of false positives outweighs the potential discovery, you hold position. The ship would decide which instinct got the better bet. Dragging magnets across an alien trail. They sailed out of Lorengau with a map that wasn't a map so much as a probability smear, an elongated ellipse sketched from wind fields, ocean currents, and a reconstructed terminal path. North of Papua New Guinea, the Bismarck Sea looks calm from orbit. Up close it's choppy, with crosswinds that shove surface water one way while deeper currents carry silt another. Loeb stood on deck with a laminated chart, transects spaced like rungs on a ladder across the predicted fall corridor, plus control lines outside it. If IM-1 shed droplets, the corridor should speak louder than the controls. The rig was simple by design. A sled framed stainless steel to minimize stray iron carried rows of powerful magnets wrapped in Teflon. The ship towed at a meter above the seabed to avoid gouging coral or stirring clouds of sediment that would drown the ketch. Every few kilometers, they hauled the sled aboard, peeled the magnetic sleeve, and washed the clinging grit into labeled jars with ultra-pure water. Deck hands learned a new rhythm: tow, lift, rinse, log, repeat. Each jar carried a GPS tag and timestamp, building a chain of custody that could survive a skeptical reviewer's red pen. Day one produced a discouraging truth: the ocean floor is loud with history. The magnets pulled up black grains by the spoonful, industrial fly ash from decades of combustion, brake dust from ports, and micrometeoric spherules that fall globally every day. Under a hand lens, most beads looked like dull pearls in shades of gunmetal, a millimeter or less across, with smooth skins and occasional flow lines frozen as they cooled. The question wasn't whether they'd find spherules. It was whether the ellipse had more of a specific kind. A micro-story unfolded at the sorting table. A technician dabbed a bead onto a sticky carbon tape, tilted it under a microscope lamp, and said, "This one's different." It gleamed less gray, more steel, harder to scratch. They started classifying by reflectivity and magnetization strength, separating the high iron, high nickel fraction from the sootier background. When they plotted counts by transect, a pattern hinted through the noise. Yields of unusually metallic spherules ticked up along the central rungs of the ellipse and fell off toward the edges and on the control lines. Not decisive, but enough to push for longer tows down the center. Back on shore, the lab work began with the basics. Scanning electron microscopy mapped textures. Some beads were featureless glassy spheres. Others had dendritic crystals, quench patterns that tell you how fast they cooled. Energy dispersive X-ray spectroscopy read the elemental mix, mostly iron, with nickel in the single-digit % range and traces of magnesium, silicon, chromium, and manganese. That by itself doesn't scream interstellar. Many cosmic spherules carry iron-nickel signatures, but a subset stood out for their hardness and the tightness of their microstructure. Fewer voids, less vesiculation, suggesting formation at high temperature and pressure. Then came the more careful assays. They ran inductively coupled plasma mass spectrometry to chase trace elements down to parts per billion. Some beads showed elevated nickel-to-iron ratios compared to typical anthropogenic slag, and a few carried unusual patterns in elements like beryllium and lanthanides. The team flagged them for isotopic analysis, the true fingerprint. Oxygen isotopes can separate terrestrial contamination from extraterrestrial spherules. Iron and nickel isotopes can hint at parent body processes. Early runs were noisy. Contamination loomed as the constant antagonist. A flake of ship paint can masquerade as a signal if you let it. Critics didn't wait. Metallurgists noted that ship exhaust and steelmaking byproducts create spherules with iron-nickel compositions all the time, some of them remarkably spherical and hard. A photo of a bead proves nothing about where it formed. Others pointed to the magnet sled itself. Any abrasion could shed microscopic particles that look exactly like what you're hunting. Loeb's team published their contamination controls: blank tows with the sled suspended above water, rinse water passed through filters and tested, duplicate samples processed in independent labs. They logged that the stainless hardware was low-carbon austenitic steel with known composition, and they subtracted any signature matching it. Composition told an ambiguous story. Strength told a sharper one. The spherules that ranked highest on their internal hardness scale also clustered along the predicted corridor. Under nanoindentation, some resisted deformation more than typical cosmic spherules cataloged from Antarctic snow and deep-sea sediments. That didn't prove engineering, but paired with the due inference that one held together unusually deep, it kept the hypothesis alive. This parent body, if these beads come from it, wasn't crumbly. Meanwhile, the mapping effort paid a second dividend: abundance gradients. Along one 10-kilometer transect near the ellipse's center line, counts of the hardest, brightest spherules doubled relative to parallel lines 20 kilometers away. Loeb framed it as a likelihood ratio. If background were uniform, what are the odds of this clustering by chance? Not a slam dunk, but enough to justify a second expedition with a refined grid and a sediment core to probe below the surface layer and date layers by radionuclides. If a spike sits at the depth corresponding to 2014 deposition, the case strengthens. The human moments kept it grounded. At midnight, with the ship rolling, a grad student fumbled a vial and watched a week's work skitter toward the scupper before a deckhand snagged it with a wet glove. Someone taped a note to the lab fridge. No coffee near the mass spec samples. On a satellite call, a reviewer said, "Publish the methods now, the interpretation later." And for once, everyone agreed. The story could unfold in pieces without forcing a headline. Composition was still murky. Isotopes take time and extraordinary claims age poorly if rushed. But the field data, where the beads were, how many, how hard, hinted that they'd traced an invisible rain to a thin line on the seafloor. The shock didn't come from what the beads were made of. It came from what they might have survived. Stronger than it should be. The clue didn't start in a lab. It started in a light curve.